So moving on to just a little bit of additional knowledge on larger rings. We've gone up and we've talked a lot about cyclohexane. We've talked about cyclopropane, cyclobutane, cyclopentane, and again, a lot about cyclohexane. There are, of course, larger and more complex rings, and the conformational analysis of these rings can be more complicated. So we're not going to really go into the depths of conformational analysis here. But generally, some of the basic principles apply when you think about them. You want to minimize torsional strain, so avoid the eclipsion of those carbon-hydrogen interactions, and minimize van der Waals strain by keeping groups as far apart from one another as possible when you're folding these rings. There are also polycyclic ring systems. Polycyclic ring systems are any ring that contains two or more rings, and they can be classified according to the number of rings they contain. To calculate this, you can use this idea that they are equal to the minimum number of bond disconnections that is necessary to generate a completely acyclic structure. That means a structure that is not cyclic. So for example, how many rings are in this? We already know this is cyclohexane, and it is just one single ring. But the idea is that if I were to dissociate one bond, this would suddenly look like this, and notice that it now is no longer a ring. And if I was to do that at any position, it would cause it to be a ring. So here, it only takes one bond dissociation, making it a single ring. Here we have animantane. Now notice if I disconnect animantane here, there's still a ring here, and there's still a ring here. So it is not completely acyclic. So now if I take out another chunk like this, you'll see there's still something cyclical in place. So one more chunk. Now you can see that the way that this has been dissociated leaves it so that there's nothing that is cyclical. It took 3 breaks, making it a tricyclic compound. There are also different types of ring structures. For example, if you have 2 rings that share one carbon in common, as shown here, we call this a spiro ring. It's usually named using spiro in its name. You can also have rings that are fused. This means that 2 rings share 2 carbons in common, as shown here in the cis bicyclodecane or cis decalin. Notice that there's a carbon here and a carbon here that are shared between the 2 rings. This is called a fused system. We can also have a bridged system, and this is any ring that shares 3 or more carbons in common. So here, you'll notice that if we count the smallest amount of carbons shared, that would be 1, 2, 3 here between the rings. So if we were to imagine this bicyclooctane, there'd be a ring here, and also a ring here. This is again called a bridged system. We also can have rings that are called heterocyclic compounds. Rings that contain one or more heteroatom are heterocycles. So these are things with oxygen within the ring or nitrogen within the ring are good examples. You will see these commonly in biological molecules. So things like nucleic acids, in our DNA, you'll see these rings, ADP, ATP. When we get into biochemistry in general, you're going to be seeing a lot of heterocyclic molecules. Also, sugars are heterocyclic. So things like glucose and sucrose and fructose, those are all heterocyclic rings. They're all rings that contain a hetero atom in it. So things like glucose, for example, have oxygen in them. Now, these conformations can still resemble what you see in carbon rings. So here's a six-membered ring, but it has a nitrogen in it, and you can see that it still goes through the same conformational ring flips changes that a regular cyclohexane would. Now, I've compiled this list here because I know within chapter 3 that there is a lot of vocabulary. We've talked about a lot of new words, and so I compiled a list to kind of get you thinking about some of the words you should be focusing on and making sure that you are familiar with. So we talked about Newman projections, and definitely know what within a Newman projection is an eclipsed versus a staggered. And then also understand that within staggered category, you can have something that is gauche or something that is anti. So again, understand all the differences in those words. We've also talked a lot about different isomers. We've talked about conformational isomers or rotational isomers. These are something that are still the same compound, but have just been rotated in a different manner. This is like the example between axial and equatorial positions. We've also talked about constitutional isomers, both in this chapter and in past chapters. Constitutional isomers are different than conformational isomers. Constitutional isomers is where you have the actual different placement of a bond, right? So bond positioning is different, not just rotation along a bond. We now also introduce the concept of a stereoisomer, and we're going to be talking about stereoisomers a lot more. A stereoisomer is something where you do not have a difference in bond placement, but you have a change in the placement in space. And one example we talked about was a geometric isomer. This is where you have a cis or a trans version of something. We talked about this in the case of rings, where you have fixed rings where their hydrogens can't rotate around the carbon. And so things that are in the same plane are cis, and things that are in the opposite plane are trans. And of course, we've talked a lot about cyclohexane and used a lot of new vocabulary talking about positionings of cyclohexane and just its general conformation. So understand what an axial position is, an equatorial position, and distinguish that from an up or down position. You should also know what the conformation of a chair cyclohexane means and looks like, and also what a boat position of a cyclohexane means and looks like. So again, here's some vocabulary to make sure that you know as we go forward in this class.